Okay, go ahead.
Okay. So today, hi all, and today I want to present a paper by Choi and co-authors, and this paper is about the Koopman AutoEncoder via singular value decomposition for data-driven long-term prediction. Maybe I will. Oh, here. Do you see all the screen or the presentation or not?
We see most of it. So if you can remove the top header, I don't know, maybe
Top header.
to the screen.
Okay, I will.
Yeah,
This
that's
is
better.
okay.
That's
It's
better.
better.
Yeah.
Okay. I tried to do maybe. Oh, okay. It should be better, but I don't know. Okay. So. Okay. First, the motivation. So our author motivate their work that the reason that the many non-linear system like I don't know fluid flows exhibit quasi-periodic long-term behavior, and the traditional data-driven forecasting models degrade over long horizon due to the accumulation of the local linearization error. So the authors want to apply the Koopman operator theory, which basically allows linear modeling in a lifted observer space. So they have the problem connected with instability in eigenvalue magnitudes, and this leads to the exponential error growth or decay in prediction. So basically they want to develop a training method that can stabilize this prediction by shaping the Koopman spectrum through the singular value decomposition. And it was the motivation. And they put some objectives. So the goal of the paper was to improve the long-term prediction performance of these Koopman-based models. And the main challenge was connected with the fact that eigen decay causes instability in long-term dynamics. So they put the hypothesis that keeping the singular values near one constrains the eigenvalue near the unit circle. As a method, they choose decomposed the Koopman matrix by decomposing of singular values during training. And maybe I should start with this: what this Koopman operator is. So they this consider a discrete time dynamic system defined by the map F, where M is the state step. And rather than studying how this state evolve, Koopman theory considers the evolution of observers, so the function G. And the Koopman operator is linear operator that evolves observers. And this means that instead of advancing this x forward and the evaluating g, chi is applied to the g. So the key advantages is the fact that even if the function f is nonlinear, k is always linear. K is linear. And because maybe you don't see all this, sorry, the screen. And in that case of action of k can be represented by the matrix.
So in which sense K is linear? Because K is operator acting on functions.
Yeah.
So it's not. So in which sense is it
But
linear?
this operator is linear, yes. That and this can allows us to observe this evaluation of observers, yes.
Well, that's what I'm trying to understand. So in which
Okay.
sense? Because this equation that you wrote, kg of x equals to
Yeah.
jf of x, it seems like we want to solve it and find k. And so k is operator acting on functions. And you're saying that this operator
Yes,
acting on,
linear.
yeah, I'm not sure I understand in which sense it would be linear. Maybe you want to go to the eigenspace of
Yeah.
functions, and then it will be acting as a linear operator on this eigenspace of functions. Okay, maybe we'll see the details there, but for now I don't
Okay,
understand.
so maybe I should
Sure. Yeah.
show the next what was in this paper, so
Mm-hmm.
maybe it will be clear.
Mm-hmm.
Uh, so as I understand this paper, of course, yes, this
Sorry, this looks, this is what we do in physics, right? So you can evolve a state or you can evolve operator. So in quantum physics, we have a Schrodinger picture where you evolve a state, and you have Heisenberg picture when you look how operators evolve. So maybe it is similar to that, but extended for more general maps. But okay, go ahead. Let's see.
uh, okay, okay, maybe
Mhm.
now it will be greener because they this what I as I understand. This is
Mhm.
they propose a concept of this Koopman autoencoder,
Mhm.
and uh, to model this nonlinear dynamic system using linear dynamics in the transformer space. So the state of discrete time nonlinear dynamic system are evolving through this equation,
Mhm.
and this operator Koopman operator theory assess to existence of the infinity dimensional linear operator. So that
Oh, infinite
exists such
dimension.
a,
Okay, now it makes sense
yeah.
because it's infinite dimension. Yes. Okay.
Okay, so
It's a space of
that
functions.
exists such a
Yeah.
operator
Yeah.
that for any observed function we have such a equation, yeah. And
Mm.
the key idea is to find the bending of the state into the space where this dynamics is linear.
Mhm.
It is I hope it is understandable. So this was the idea of the authors. So this is this autoencoder, yes. So we have the encoder that approximate this observed map G. We have the coder that approximate in the inverse map,
Mhm.
and the matrix chi that approximate this Koopman operator. I don't know how to say in English this chi. It is not the same chi. Okay, this
Calligraphic K.
calligraphic chi. Okay, thank you.
Looks like it's calligraphic.
I think so.
Yeah.
I think that okay. So this I think this is the picture from this publication. So they have a little bit collision of the for variables. I think, but
Mm.
I think that this K is matrix. I believe so
Mhm.
here. But- okay, and. So, what kind of architecture is of this autoencoder? So I think that encoder observed the learners, which is described with Z, and that captions essential system behavior. Then we have this Koopman matrix, and here which governs linear evolution in the latent space. And then we have the coder D that reconstruct the predicted physical space. Yes. So for example, when we have M5, the encoder is five, I don't know, let's say abstract nonlinear features, which evolution is linear under this K, which K is this Koopman operator. I believe so. And this feature from this, in this case, 5-dimensional approximation of the Koopman invariant subspace. It will be.
So I'm lost again. Can you go back to the previous picture?
Okay.
I don't quite
So
understand.
this
So your evolution goes from x at t to x at t plus 1. So this whole autoencoder is what nonlinear evolution is, right? From t to
right.
t plus 1. Now, from I understood, the Koopman operator has to be applied to the function, and then not be inside of a function. So it has to be application on a function that will tell how the operators change, observables they call it. How certain observables change. Where they are observed, or are you saying that maybe all of the observables are sitting in the bottleneck, and maybe we are just going to evolve those observables that are in bottleneck? Maybe that's the idea. Because
I think
here they're just putting a matrix in the bottleneck, and then they call it
yeah,
Koopman autoencoder. That's the only thing that is different.
this is the only thing.
Yeah,
And
because
this is and
but we have
it's
those
an only
matrices
it is
anyways
linear.
in the standard autoencoder. I mean, we don't isolate them, but they're matrices that go from one layer to another, so they're still present there. Um, so I'm not clear how that differs from the regular autoencoder architecture.
Maybe they want because they want the operator to be linear.
Well, every time we have a matrix in between layers, it's linear, and it's our choice to make transformation on the neurons non-linear. We don't have to. We can keep it
Yeah.
them linear too. We can, you can add linear layers in your architecture. Then there's uh, okay. Well, maybe once we see examples, we'll further
Okay.
clarify it. But for now, it doesn't seem to be like anything different from what we
Something new.
usually do. Yeah.
Okay. So we go the and next the multi-step prediction is obtained by iterative latent dynamics. So it is and however this once moment because I'm lost. Okay. They because the objection of this paper was also because out here was written because they have a problem with here entering spectral stability. So the eigenvalues and so on are crucial but difficult to impose directly, and they wanted to do it. So maybe it was this was connected with the fact that they proposed this Koopman operator. Okay, so we go next. Here we have the multi-step prediction by iterating this
No, I
latent.
think this is crucial, Agnieszka. So I think this answers my question. So this
Okay.
first equation there. So basically, you're saying that they're saying that evolution in time to multiple steps can be done by executing encoder only once, then linear operator tau times, and then decoder only once. So basically, all of the evolution part is just really sitting in the bottleneck, and the encoder and decoder is just to to go to that place. So no, now I see the point. Now I see why it's called Koopman, because really you're putting all of the relevant observables into bottleneck and latent space, and then you do evolve there completely linearly. And then you're going to be training it this way. So basically, you're going to probably be training it for different taus. That makes
Yeah.
sense. Okay.
Okay.
Good.
And in the next they have the problem with stabilization of these predictions of the with the learning, yes, because the learning was unstable, I believe. And here they introduced consistency via inverse dynamics, tak? Yes, they introduce an approximate inverse operator G. So G is an inverse of K. And the idea was not that only K should evolve Z forward, but also G should recover from the Z from the step T minus 1 from Z to T.
Yeah, so it should
Yeah.
go forward and backward in time. It should be like yeah, unitary operator that propagates forward and backward in time. That makes sense. Yeah.
So to ensure this, they introduced the consistent regularization, and this encouraged bidirectional consistency with the latent space. Yeah, so this helps to prevent grow or decay in the long-term prediction, and it is essential for modeling this reversible or quasi-periodic dynamics. And it was and next and they proposed that instead of directly constraining these eigenvalues for key, they use singular value decomposition, and this helped to prevent the long-term instability in prediction. They regularize these singular values, and this encouraged K to be approximately normal preserving. And moreover, they also regularize the orthogonality of function, and here we have the full spectral control term. And next, it was maybe to be hard. They wanted basically to putting all this together. Yeah. So they're starting to say what they want to do. So they have a normal encoder. How to, they say how to develop this encoder, and finally to have some numerical results. They put it all together. Okay? So this is the scheme of the pair of this autoencoder. So this is this two auto encoder with forward and back forward prediction. So this solution integrates this Koopman dynamics about I was saying before. Also integrates spectral stability through this regularization, SVD based regularization, and temporal consistency through the inverse dynamics. Yeah? So as a total objective function, it is very complex, because they want to jointly learn a Koopman in invariant representation. and ensure long-term stability of the latent dynamics. So the objective was here. It is written here, and we have the first part is training it. This trains the encoder and encoder to reconstruct the input, and the second trains key to approximate the latent time evolution. This one uh, is promoting reversibility and stabilization the latent dynamics. So and the fourth part of the equation is to avoid the exponential growth of decade, and the last one, which is very complex, mm, making this computation stable. And what they do, and they have tunable waves, so each omega scales it in the corresponding term, and for example, large value of omega f emphasize accurate forward prediction. When we have this omega SVD large, this prioritizes spectral regularization. And when they choose the balance wakes, this ensure accuracy and stability. So uh, and uh, finally they have make some numerical results,
Mhm.
and they evaluate this let's say autoencoder and the learning type with the state of the art baselines. For it was the vanilla KI C of and ISVD CKAA autoencoder, and okay. And these experiments demonstrate this architecture that they propose can improve this long-term prediction accuracy and stability of this network architecture. So here we have the plot of the lost curve evaluation during the training in this proposed method, and here we can see that long-term prediction, so here is 1000 steps, is closely matches to the true trajectory in the 3D latent space. So stability is maintained across different loss weights settings. Yeah. So for example, when we have at the beginning the computation are not so stable, and when we go with the steps, the computation became very stable. It was the first. Then they show us the prediction accuracy and costs. So here we have comparison of the predicted and grounded true for 100 steps, and B, we have the evolution of the predicted error from the I believe from the different values of the omega, and then they propose as the visualization of the eigenvalues. So basically what we can see from these results, so that vanilla and CKAI are faster but suffer from the higher error. Maybe it is not so visible of this plots, but it was written in the paper and in the other results that they show us. And next they also show us the prediction error. in the tables. So here we can see that vanilla. That what I was saying, that vanilla and CKE are faster, but they are suffer from the higher error. And then they also show the robustness over the time. So here we can see the gap windows as prediction horizon increase. So this approach USVDCKAE with the very long shortcut that they proposed is have very small prediction error, and this is from the 200 epochs, and the other cases which are baseline have the higher prediction error. So and for example ESVDCKE is also accurate, but is more computationally expensive. So maybe I tried to summarize what have been done in this paper. So the authors developed the improved Koopman AutoEncoder architecture, and it was this improvement was connected with the incorporation of the singular value decomposition. And next, they replaced the direct eigenvalue control with control over singular values through the differentiable loss function. So they proposed the special shape of the loss function to replace this direct eigenvalue control. And then the unitary structure of the Koopman matrix was enforced through the orthogonal constraints in U and phi and Y. And at the end, the consistency of back-forward dynamics was introduced by approximating the inverse Koopman operator. So they wanted to put all this in one autoencoder architecture. And maybe some conclusions, that is that this Koopman theory allows no linear dynamic system to be modeled as linear system in a lifted observer space. So they show us that it is possible. And this Koopman autoencoder use neural networks to learn these observers and approximate the Koopman operator with a fine dimensional matrix K. Spectral stability is crucial for long-term prediction and ensuring key behaves approximately like a unitary operator. They also use singular value rate decomposition, which enables smooth different table spectral control by enforcing singular value rates be close to the one, and promoting near orthonormality of Koopman modes through this UNV. And finally, to summarize this architecture that they proposed supports the hypothesis that accurate stable long-term forecasting is partially for the quasi-periodic and energy conversing systems. So thank you for attention.
Thank you, Agnieszka. See if there are questions. I certainly have questions, but maybe somebody else has questions.
I do have one, actually.
You can have two, Diego.
No, it's
Not three.
like this is very. I don't know anything about Koopman matrices and stuff like that, but like I noticed that they use like fluid dynamics and stuff like that to test these things. And like, can we get like physical interpretations for the stuff the encoder does? Like, or are those things like lost in the black box kind of way?
No, the only interpretation, sorry, I jumped right in physics. So, so the only interpretation I see is that, that's how we evolve, for example, wave function using a unitary operator. And you can evolve the wave function or you can evolve operators, right, using Heisenberg equation. But the problem I have is that not all the systems can be evolved this way. So not all the systems are unitary in a sense, or can be linearized this way. That's where I get confused because the operator has to be a linear operator in infinite dimensional space. So really, for this to be useful, somehow the relevant observables have to form some finite dimensional subspace. And then you may be able to do this. But you cannot do it in general. So that's why. So I guess we can look, but there is a test to this, I thought. So they have this inside in the bottleneck, they have linear operator. And then when you want your state evolve over tau steps on time, you just raise this operator to the power tau. And if you want to evolve backwards in time, you raise it to the negative power. So, but why not put there, unconstrained network, some nonlinear transformation? Now, will it make it better? If it makes it better, then I guess then that's not completely linear evolution. So, yeah. So in this latent space, instead of putting a linear transformation, you can just put a nonlinear, like unconstrained network or a singular neural network, something like that. But yeah, I'm a little bit confused when it will work. So for what kind of system it will work and for which kind of system it will not work. It cannot work for all systems, but probably for some where relevant observables form a finite subspace, maybe there you can do that.
So maybe they want to do it to the to check this according to the baseline, the network with structure like vanilla and so on. So they wanted to propose something that should work better from this concrete cases.
But it cannot. My problem is that it cannot work for all data sets.
Yeah, this is true.
If it does, then it's very, very strange. All temporal data. Now, of course, they're talking about temporal data when X evolves with time. Okay, but I don't know. Just take three coupled oscillators, three body problem. I don't think you can make it linear. I don't think you can linearize it this way. This is any chaotic system.
Maybe it's limited to like situations where it's in a periodic solution stuff, something close to it.
Well, it has to be effectively linear somehow. So okay, maybe periodicity gets you there. So if you go through, but even there, we know that Hamiltonian systems are periodic, right? So you can have a periodic system which will come back to where it started, but on the way there, it can experience lots of non-trivial, non-linear behaviors. So I guess I still don't understand really the range of applicability. I think it's a very good idea to linearize the dynamics, like, put everything that's non-linear is encoder and decoder, and they'll live in the bottleneck on the linear part of it. I mean, it's a great idea, but I just don't know when it will and will not work. Maybe that's kind of open-ended question. Other questions, comments, suggestions? All right. Thank you, Agnieszka, and I'll see everyone next week.
Thank you.